And then move these things aside. Does it look okay over there? We'll see. Once I start typing, we'll see if the font is large enough. But let me just give you a tour of the hub. When you land into the hub, you should see something like this. I have a few more folders than you should have, but something like this. This docs will take you to like all this documentation stuff that we showed you yesterday. Like there's a updated schedule over here of this week, next week, and we can update that if things change. There's some maps, the slides from yesterday. This one's useful because it has links to the various Zoom rooms. I won't click on any of these right now, but if you go into the hub and you go to this docs and you open up this .ipynb file and click on one of these things, it'll take you to that Zoom, or open up Zoom on your computer. So that's useful to have. There is a folder called curriculum that should include materials for many of the lectures, although not necessarily this lecture. I'll explain in just a minute. You should have a folder called shared. Shared includes the docs folder, but it also includes place for data. So there's a bunch of data in there right now for things we'll teach this week. And next week, if you want to put some more data in there, you can ask us to do that. The shared folder is read-only, and Noah and I have also a shared read-write folder in which we can write. So it's intentionally not meant for you to write into, because if all of us start writing in there all at once, we will run out of we have ample space in there, but we will run out of it. So if you have data requests, they should go through us. That's mostly next week. This week there won't be any reason to put data in here, but next week you might come up with some ideas about data sets you want to work with, and you'll want to have those accessible. We'll talk all about data sets also on Friday in this data showcase. We'll show you some ways to get access to data that actually don't even require you to put data into the hub. You can get them from wherever they are and read them straight into your Python process. But that's on Friday. Okay, so this is what it looks like. Kind of we land in there. You should have a window that looks like this. So this is called Jupyter Lab. Those of you who've used Jupyter Notebooks, this is, and haven't seen Jupyter Lab, it's a little bit of an elaborated interface around Jupyter Notebooks that allows you to do things like launch notebooks and run them, but also allows you to open a terminal. So if I click in the launcher on terminal, I get a terminal window straight into the Jupyter Hub. If you look around PWD, we're inside of the environment that's in the hub. Each one of you actually has a separate environment. If you type "who am I," you'll see that we're all Jovian, which is the name of the inhabitants of the planet Jupiter. So it's natural that we would all be Jovian, but we all have the same username. We're all in kind of little isolated environments. The only thing that's not isolated from each other is that shared folder, which is shared. So if somebody puts data in there, we put data in there, everyone can see that, but no one else can see the contents of your home directory. You each have a home directory that all have the same username. So we're good. If you click on this plus, it opens this launcher window. You can open the Jupyter notebook right in here. It opens it as untitled.ipynb. Who here has seen Jupyter notebooks before? Okay, so I don't need to say a lot, but you can write Python code and execute it in the Jupyter notebook. And you can organize things. There's a file system here, so you can organize things into the file system. So maybe it's not so nice to have your notebook called untitled. Maybe we want, I'll start sort of going into the materials. Maybe I have my project, or maybe I have a project. This is actually what I have. Okay, thanks. I have a projects folder, and then this I might have like a folder called blob calculations. Is that big enough to see where you're sitting back there? Yeah, okay, good. Blob calculations, and maybe that's where I'm calculating something about blobs from my data, and maybe I'll move this, I can cut it, and I can go and I can paste it in here. lets me organize. So later on, when you start working on various things, it'll be nice to organize things in some reasonable way. Maybe I don't call this untitled because that's unseemly. I'll rename it to, what is today, 07. This is how I organize my projects. It's the 29th. Blobs. Okay, so this is pretty typical workflow for me. I have a projects folder in my computer, and I have various projects in there. And in the projects, it's actually quite typical for me to have a big old pile of notebooks with dates, so that I remember when I did things. And inside that, I'll write some code, and I'll do various calculations, visualizations. I'll use Jupyter notebooks the way they were intended to calculate all kinds of things. And I can imagine that this resembles in one way or another a workflow that a lot of you use when you use Jupyter notebooks. They're really great for ad hoc data exploration, for calculations, for communicating with others. You can write all these complicated narratives with notebooks and share them. They render online on GitHub in a way that you can then send to somebody and show them, this is what I did. And that's very, very nice. Okay, but the problem with this is that a code that gets written in a notebook is pretty much locked inside of that notebook. If you want to execute it somewhere else in a different notebook, you would have to copy paste it into this other notebook. If you wanted to share it with somebody else, you'd have to give them that notebook, and they would have to go and take that piece of code and copy and paste it into their notebook. And that poses a problem. This is not good software engineering. This is not how we'd like to work. We'd like to create reusable code and share that code with others, be able to use that code. Well, first of all, be able to use that code over multiple different notebooks within a project, for example, and then use it across multiple projects that we're working on, and eventually share it with others so that they can use it as well. And this lecture today is meant to show you that series of transitions. So the hope is that this will fit into the model that you have of how you work, in the sense that you start in a notebook maybe. How many of you actually use notebooks for like data analysis on a day-to-day basis, just out of curiosity? Okay, so a lot of you. Okay, good. So this hopefully will fit into your kind of mental model. I'm working in a notebook, and I'm going to make this into something that I can use over multiple notebooks, and something that others can use as well. Out of curiosity, how many here write code that others in their lab use? Okay. How many here write code that other people they don't know use? Okay, a couple of you. Okay, good. So some of you are familiar with some of this. Hopefully you'll still, the goal of this really is not just to, shouldn't say just, is there's a tendency in programming to do what's called cargo culting. Anyone familiar with the idea of cargo culting? The idea of a cargo cult, it's taken from an observation that anthropologists made in the South Pacific Islands. I don't know if this kind of how I received this, so take it with a grain of salt, whether this is an urban legend or not. But the urban legend at least says that anthropologists in the South Pacific noticed that people in those islands would create all kinds of structures that looked a lot like airplanes and like control towers. And they sort of asked them, what's the story here? And they said, well, when these things appear, then food appears. And that's because during the, I think, Second World War, there were a lot of cases in which airplanes would drop cargo with food onto these islands for the soldiers fighting on both of those sides. And they said, if we create these things, then food will show up. And so the idea of a cargo, and the anthropologists named these a cargo cult because they were cults devoted to cargo. They didn't really see that the cause and effect here. The thing that caused the food to appear was not the structures and things that look like airplanes. It was other things. But we do this a lot in programming, where somebody gives us something and says, this works, and we kind of copy it. We copy all the structure around it. And this is particularly true in Python packaging, because it's like an obscure topic a little bit in engineering, and it changes, and it's kind of weird. So what I have done for many, many years is, here's a package that works. I'll copy it and replace the code in there with my code. And it took a long while for me to actually understand what the different pieces do. So the hope is today to describe to you, like, okay, this is the mechanics of what these different pieces do. And the reason that there is not a relevant folder in here for this is because a lot of what I will be describing is in a book that Talia Arconi and I wrote. So we wrote this book called Neuroimaging and Data Science based on our experience teaching in NeuroHackademy. The book is, there's like a bound thing that you can purchase, but the content is actually all on this website too, so you don't need to purchase it. And in fact, this particular chapter in the bound thing made out of dead trees is outdated by now, and this is up to date. So you should refer to that. And I have a printout here, so I'll use that, and I'll post this to the Slack channel here, so that you can refer back to that. I'll kind of walk through and maybe improvise a little bit based on this, but this is kind of the material that I'm going to be going over and is all about sharing code with others. Okay, so let's go back to motivation a little bit. Why would you want to share code with others in the first place?
To collaborate.
Say that again, please. Sorry.
Collaborate with others.
To collaborate with others, yeah, that's a primary cause. If you want to collaborate with others, then it's kind of a necessary step that you write code, they can run. Okay. Other reasons you might share code with others?
Well, reproducibility.
Reproducibility, you write a paper, you've written some code along the way, you want others to be able to reproduce what you did. The code is kind of a necessary piece in that.
Redundancy, we have to do the same things over and over.
Yeah, so that's kind of like an engineering principle. Don't repeat yourself dry. Yeah, so kind of reduce redundancy across maybe a lab or an entire field. Other thoughts? Fame and fortune. Only halfway kidding here. Okay, and then so the question is, when you're working, what should be shareable is a little bit amorphous. And at least when you start working, at least when I start working, it's not obvious to me always like what bits of what I'm writing right now should be shareable. And we'll come back to that a little bit later. But let's look at the mechanics of this. Let's imagine that I am working on a project and I have some code that I'm writing. Looks something like this: from math, import pi, import pandas as PD. And you don't necessarily need to write this code on your end. This lecture is actually going to be less on like you doing hands-on stuff, although later on you want to practice this. But definitely follow along as I do this. Read CSV. I don't know. Maybe I have a folder in here, input data, raw, blah, CSV. This is all pretend because this file doesn't exist there, but and I'll show an intentionally very simplistic example here of something that is not exactly what we do, but is not that far away from it. I'm typing it in so that you can kind of see what all the pieces of the code are. Okay, so this is, in some sense, this is like every project I've ever done. Yes. Like that, it's good. Okay. This is like every project I've ever done. In Python, there's some imports at the top to use some external libraries. There is some data somewhere. I actually have been trying to follow this kind of structure again in my projects where I have a folder that's data, and then there's raw data, and then there's maybe like data derivatives, actually, is what I usually do nowadays. And this raw data will be like the stuff that I got from somewhere else that I don't touch at all. And derivatives will be something that's generated by code that I can point to in that repository. So that's also kind of like best practices maybe in, or reasonable practices in project management. But kind of like I read the data in from somewhere, I extract some properties. This in kind of data science sometimes is referred to as ETL, extract, transform, and load. Then I do some calculations on this. This might be the transformation. Then I save out some results. Maybe there's some visualizations also. But so what's the problem with this?
Points to a directory that's.
So it refers to very specific kind of code locations. Actually, this is not too bad. At least I didn't write like home, Jovian, right? So it's a relative reference. So, whoever gets this repository and also the raw data will be able to reproduce this. So one of the problems with this is that it does what is called mixing concerns, or it does not separate concerns. This is also kind of like an engineering principle, the separation of concerns. So there are different concerns here. One concern is about file and data management and interactions with the file system up here. There are numerical calculations that go on here. In fact, there are two separate numerical calculations that happen one after the other, and that are, when you look at them, they're completely independent of each other, right? The result from the first calculation is not used in the second calculation. So these are two completely independent calculations. And then there's, again, some data management stuff over here and some interactions with the file system here. So when we write this kind of code, we'd like to exercise separation of concerns, separate as much as possible, and modularize our code as much as possible. So our first step then might be to identify pieces of this code that we can modularize into functions. And Python makes it very easy to define functions. For example, I'm actually going to do this the way I usually end up doing this in Python. I split the cell up, and then I add another cell down here, and this is where I would usually define my forgot to return. And then once I've done this and I've sort of modularized out these functions, I can replace these calls here to numerical computations with calculate area with my blob radius and calculate circ with my blob radius. And this is actually the process that I go through. I go through and I start writing some code and I do some calculations, and then I realize, oh, there's a function right here. I'm going to use this again somewhere, in this notebook. Let me put it in a cell at the top. So I'll have a cell at the top with my notebook with function definitions. And initially, at least that's how I'll go about kind of keep working on this, and then the functions will get more elaborated. So this is fine per se, but there's a lot more facilities that are provided by Python to make this even nicer. One thing that you can do is to add documentation. It's a good idea to add documentation when you write functions. For this one, for example, so what Python allows you to do is when you define a function, if you insert immediately after the function definition, the first line of the function, you insert a multi-line string, that multi-line string becomes attached to the function as its documentation. We'll call that a doc string. So I'll demonstrate that. Calculate area of a circle. If I run that, now I have a function calculate area. It's an object, it's a function, it's defined inside of this kind of like the main loop of this Jupyter notebook, and it has a dunder doc attribute. Okay, this is the time to talk about dunder attributes. So dunder attributes are attributes of Python functions that are often generated by Python, the language itself. These are not things that you usually assign. They're attributes of the function that we think of as private attributes that are assigned by the system. And they're not different from other attributes of an object. This function here is a Python object like any other Python object, and it has various attributes. And one of these attributes is this double underscore doc double underscore. And in order not to have to say double underscore something double underscore, I will refer to it as dunder. So that's where that word dunder comes from. It's double under on both sides. And these are all kinds of things that for example, for an object of a type of a function, there will be a dunder doc that's associated with it. In this case, it's the thing that we wrote down here. And that we can use that in all kinds of ways. For example, Jupyter knows how to use this because if in Jupyter we type calculate area and a question mark, it will type out the doc string here. Okay. And it's a good idea to write these doc strings, type out this, following a very particular way of writing doc strings. And that's the way that's defined by the NumPy docstring standard. This is in the NumPy style guide. NumPy, the numerical Python library, that's sort of the workhorse of all of numerical Python, pretty much, has this. That's the wrong place. Right, has a docstring standard. Maybe I'll just put that in Slack right here. And it's a good idea to follow this docstring standard. It tells you how to write docstrings, like what goes into a docstring. For example, there should be a one-line summary that does not use variable names or the function names, like I did here. Calculate area of the circle. It should end with a period. It's a sentence. And it should be one line. Then you might have a section called parameters. For example, R is float, int. Actually, probably more likely float the radius of a circle. And then there would be a section called returns. That's all written in that document. Area. And this is the basic docstring definition. Every character here matters. This is parameters, not inputs, not whatever other word you might come for parameters. There's a series of I believe it's dashes. Yes, I do this automatically now, so I don't even remember what I did. Dashes that are completely under that. There's the name of this thing, followed by a space, followed by a colon, followed by a space, followed by the type that this expects to have, and then a definition, again, a sentence that ends as the period. and so on and so forth. And the reason I pause on every character here is that this is intended to be both human readable and machine readable. And the way that this is machine readable is that the nice thing about this kind of making this machine readable is that if you write code like this and later it becomes part of a library, then this doc string can automatically will automatically become this documentation that you see here. And if we're not careful about the spaces around the colons, it might get misrendered, for example, into HTML. There's a whole system called Sphinx that is used to document the language Python itself, but also libraries written in Python that knows exactly how to take these doc strings and turn them into very nicely rendered either HTML, PDF manuals, render them into your Jupyter notebook. So now if I do the question mark, now you can see it renders it kind of in a way that you might expect. And this is nice because it's machine readable and you can render it, but it's also nice because now if you approach somebody else's library and you're wondering what it does, this is a common language that we all use in this big ecosystem of scientific Python. And because we all follow this standard, it's very easy for me to understand what somebody else did by reading the doc strings of their functions. Okay, so we can do that. We can kind of do that for this other one as well. I'm gonna copy paste here because a lot of this is essentially the same except for the so nice. I've created these two functions, and now I can use them, and I've also documented them. Documentation, the purpose of documentation is to communicate with others, but also with yourself. So when I come back to this notebook 3 months from now, it'll be easy for me to understand what these functions do. These functions are very simple, but you can imagine doing something a little bit more complicated and having a hard time remembering what exactly it was that you wanted to do. Okay, actually, let me stop here and see what questions do people have at this point.
In terms of like the strict formatting, what's the rule for like spaces or indents for the description after?
Yeah, it should be, I think it's 4 spaces here. You'd have to consult the style guide exactly on the. Yeah, and you can have things like int optional if it's iterable. There's here are kind of things that these parameters could be. Yeah, there's a lot more here. But you can see it's kind of follows this general. Sometimes the return is not defined as a variable name, in which case you need to do like, oh, this thing returns an integer instead of saying area float. So there are variations on this, and this document is actually pretty long, but this is the basic construction. Yeah.
Are there linters that will automatically generate it for you, or like a boilerplate for you, so you don't have to type it out?
No, not that I know of. Yeah, that's probably a good thing. You want to spend some time thinking about what this thing is. Good question. Okay, sorry, I should repeat questions that come in the room. The question was whether there are linters that can do this automatically, and I don't know of such linters. And I think that's probably good because when you write documentation, you want to be thinking about what it does and like what's a good description of what you did. It can help you also spot whether what you're doing is reasonable. Okay, so this is great. Now we have a notebook. This notebook, you know, all else being equal, this thing is very reproducible, right? You can give it to somebody else, they can run it. It's very clear what it does. If you want to calculate area from, let's say that you had, instead of just 1 file with blobs, you had 10,000 files with blobs, it would be relatively easy to reuse the code again and again and again in multiple places in this notebook. So that's, you've already to some extent separated concerns out. The numerical computations, instead of being embedded in this code, they're separated. We've separated the 2 computations from each other so that they're neatly can be neatly sort of addressed, refactored, elaborated. So that's that's pretty nice. What is the problem now, though? If we're thinking about a project and yes,
The function are only usable in this notebook, cannot use them in another place.
that's exactly right. So the answer here was they're locked in this notebook and I can't use them anywhere else. And so again, exactly is the way that I work usually on these kinds of projects. What the next step that I will usually do is to start a new file in here that I will call something like tools.py. And this will be a module that I use inside of this project. And I will take and I will copy these or cut these functions out and copy them into this code. I will also take out this import and I will put it here because I'm using pi from, I've imported from math, I've imported this symbol pi from this is the standard Python library math library. It includes in it definition of pi. I'll put this in this separate file called tools. And this thing is now a module. And so one of the, so it's separated. It's not in here at all. And the question is, how does it get in here? And for this, we need to talk a little bit about what happens when you type something like import pandas as PD, what the import statement actually does. So the first thing that the import statement does is to look wherever the file is in which the import statement is issued for a file, a Python file named pandas in this case, or in our case, a Python file called tools.py. And it finds locally, right there where you're running a file called tools.py, it will look for a name, it will import that. So now, oh, module name tools, that's confusing. Let me restart the kernel here just to be sure that I'm not missing something. Oh, that is confusing. Maybe it's
Your tools, Python script says it's modified next year, so it might.
why? That is so odd. Okay, let's go and understand this. Now. It was changed now. Why was it changed now? Who changed?
Area.
Calculate area. Oh, yeah. But it's not even finding the module, which is very confusing. I'm baffled. I'm confused.
In the same directory.
Start kernel.
Yeah, that sometimes helps. But I'm baffled. This worked, but doesn't work now. Let me see if I missed something. And if not, then we will.
Could it be because the tools, the script is still open? Maybe you can post the script that will see it say it.
Yeah, I'm gonna try something else here. I'm gonna try Python file. Maybe Jupyter is having some confusion because it didn't start it as a Python file. It shouldn't, but let's leave it untitled and see if untitled. No, not expecting. But this next year is also quite confusing, right?
Do you not need like an init file or something?
Not typically in this situation. but let's add an init
You
file.
can use sys.path.append.
Yes, I could, but I didn't think that I needed to. But we could do that. So, okay, I'll debug this later. But principle, this should work. I'll figure this out later. I'm not sure why it's not working. But what was mentioned? Sorry, I missed. Who said that? Just so I know.
Me, Diego.
Diego. Okay, as Diego mentioned, one of the next things that Python will do is it will look for a Python package in the current location. So the first thing I believe it should do, or maybe I'm confused, is look for a Python file in the current, or Python module in the current location. The next thing that it would do is look for a Python package in the current location. The difference between a Python module and a Python package is that a Python module is like this. It's a file. A Python file right there in that location. The Python package is a folder that includes a dunder init file in it. Dunder init file as part of its content. So if I create here, we'll try this. Let's see if I can make this work. Tools.
I just test what you've done and it's working, so maybe it's just a programming zone instead of the connection.
Maybe it is. Oh, that's happy. I'm happy to hear that this works, but why doesn't it work here? Oh, okay. Well, maybe my hub is confused. Should work. But okay, so this is one mode that I use a lot. So it works all the time, except when I'm teaching it, apparently. Which is to have in my project, I'll have a tools file, a tools.py. So let's talk about it because I think it should work. You have this tools.py. The nice thing about this is that, like I told you, I'm going to have a pile of notebooks in here because I'm going to work on this for over time. And every day that I start working on it, or every once in a while, I'll start a new notebook where I'm kind of working on something new here. And in every notebook that I write in this project, I'll be able to write import tools, and usually it'll work. And I'll be able to reuse these tools within this project. So that's kind of step one for me is I have a project. Within this project, I'm using a set of tools. Those are Python functions, maybe even classes that are defined within a tool library that I have in this project. And that's a good first step. Again, fully reproducible because it's there alongside with the code. If the code appears alongside the data and I give it to somebody else, they'll be able to rerun that. But the same kind of problems start showing up here as well, you might imagine. Maybe what's the problem with that? Maybe this is fine, actually. I guess from my perspective, the problem with this, at least for some things, is that I can't reuse these tools in another project unless I copy paste these tools into this other project that I'm working on. So if I'm working on more than one project at a time, or different people I collaborate with work on different projects that all want to use the same tools, this approach no longer cuts it because it's kind of locked into this project, right? Previously, I had it locked inside of a notebook. Now I've freed it from that, and now I can use it across multiple notebooks in a project. Now it's locked in that project, and I want to be able to use it across multiple projects. Kind of out of curiosity, who uses a workflow that looks a little bit like this, where you have like a tool library and you import into notebooks in that same, yeah. How is it different, out of curiosity, just to hear what other people are doing? Or is it just pretty much this? Yeah, okay. Yeah, and this is pretty typical and useful in and of itself. Now, in order to make this more generalizable, I need to start understanding more about what the import statement does. Like if I was here and had some tool library somewhere, how would I get that tool library how would I import from that tool library? And for that, we need to understand what's happening here. Pandas is not defined inside of this project. Pandas is defined somewhere else. It's somewhere installed on my computer somewhere, but it's not right there. Instead, Pandas is something that I can import from anywhere. And our goal here eventually is to get to the point where we will have these kind of libraries that you can import from anywhere. And we call those Python packages. I gave you a definition of a Python package, but another way of thinking of a Python package like Pandas is installed in this computer, in this environment, in the sense that when you type import pandas as PD, it will look locally for a file called pandas. If it won't find that locally, it will look for a package locally that is called pandas. For example, I started doing that here to solve my problem, but we'll come to that, back to that in a second. And then it will look into something called the Python path and look for packages in the Python path that are called pandas. So the Python path is an environment variable defined in the operating system, and it contains a list of file system locations. It's all kinds of places in the, here, I think we can see it here, import os.environ, Python path. Did I misspell it? I think this is also a place to find it. There it is. Okay. So there are various ways to find this. For some reason, it's not defined as capital Python path in my environment, but there is an environment variable that should correspond to this. And here there is a bunch of different places where this particular environment, so if I import the Python standard library sys module or library, there is a sys.path. Diego mentioned that before. He said, hey, you can add this to the sys.path. And that's true. I can actually, it's a list, it's a Python list, and I can add append, I don't know, some file system location, like maybe even just period, which means add the current location to the sys.path. And then I would be able to import stuff from there. But that's a little bit kludgy, just a little bit, actually, not terrible. Because then we're telling Python, in addition to looking, and this is ordered, it'll look in the order that this is organized. It'll look first here, then in this folder, then in this folder, and then in this folder called site packages. And those of you who have mucked around with Python installations and stuff like that have seen the site packages. Site packages is a place where when you use a package manager or in order to install a Python library from somewhere else, usually it'll go into this site packages. And I'm pretty sure, for example, pandas is actually a folder. There's a folder called pandas inside of the site packages. And inside of that folder called pandas, there is a dunder init file. And so when we type import pandas as PD, Python will go to this location, will find that folder, it'll see, oh yeah, this has a dunder init in it. And in fact, when we type import, it'll run that init file, dunder init file. Russ mentioned init files in his lecture just previously, said he doesn't like to have code at all inside of these dunder init files, but that gets run when you import something. And then you can import from that package, you can import other names as well. So this is the standard mechanism for finding Python packages, looking under the site packages. And so if we write some code, one good thing that we can do is we can have Python put it in this site packages for us. So there are various ways. Let me first do the thing where I turn tools into a package locally. Let's see if it works for me. I'm going to move this file tools in here. And I'm going to change its name because now I have tools, and maybe inside of the tools I have tools for different things. Let me call this, no, I don't want to delete it. No, let me call this circle. So this will be tools for circles. Maybe I'll have tools for other things in here as well. And let me add touch, dunder init, dot py. Let me see if I create it through the terminal. Maybe it's better. So here's the dunder init file. And then I can go back here. I'll restart the kernel. And then I will try to do from tools import circle. Let's see. Maybe I'm not in the right place. No, this is in fact in the right. I'm gonna save this one and close it and close all this and go over here and then restart the kernel for good measure and so confusing. I don't know what is broken about Python, but something is broken here. Because this should work. Let's imagine that works. I don't know why it doesn't, but there it is. So now, in principle, we can do from tools dot circle import, calculate area, calculate circ, and in principle, although not in practice on my machine right now for reasons that I don't understand, and why is it saving it next year? Who knows?
Can we see the init file, please?
Hmm?
Can we open the init? Yes. Okay.
Nothing in it.
Nothing.
Yeah, I mean, you could here do things like from dot circle import. Here's where you manipulate the namespace of your, where you can manipulate the namespace of your package. You can write code in here. You can say, you can write the function definitions right in here, but that would be really confusing because you don't necessarily expect, but you can do things like from dot circle import, calculate area, calculate circ, and then upon import of the package, this will run and it will look right there for a file called circle, and it will import those names from there. So this follows the previous rule, right? Find me a file right here called circle and import these things for me from there. And then what that would mean is that instead of from tools.circle import these things, you can import directly from tools because they're already included in the namespace of the package because they're defined in that dunder. Right? Things that are defined in here are in the global namespace of the package. Any name that is in here is directly under the namespace of the of this tools. Let me do a little sanity check here. When I say namespace, who here is like, yeah, I know exactly what a namespace is. Oh, great. Okay, yeah, sorry. Okay, namespace. Really important concept in Python. Not too complicated. A namespace are all the variables that are defined within a Python process. Right? So when I started Jupyter Notebook, my namespace is blissfully very empty. Not a lot of variables in here, not a lot of functions defined. One of the benefits of Python programming is that things need to be imported. And because things need to be imported, you know where they came from, right? Russ mentioned again this thing, you don't want to do from pandas import star, although this is syntactically correct Python, this is called namespace pollution. And the reason it's called namespace pollution is because there are a lot of names defined in pandas. In that dunder init file in pandas, there are a lot of names defined. Lots of the functions that are available to do through pandas are inside of that namespace. And if you do this, they will all be in your Jupyter Notebook namespace. Instead, you want them constrained to this. This is also a namespace. PD here is a namespace. Inside of that PD, there are a lot of names. So I can show you in Jupyter. Let me add in. One way to do this is PD dot and hit the tab key. And this will show you all the names that are defined in that namespace. And they're only inside of this PD dot namespace, which is nice because if I use, for example, PD dot data frame, when you read this code, you know exactly where this data frame came from. You look at this and you say, oh, PD, that's from pandas because you imported pandas. It's not some other data frame that you defined here. This gives you also freedom. You can define other things here as you'd like. So a namespace is all the stuff that is defined within a per certain Python process. And here, the namespace is the namespace that gets shoved behind this period into the tools package. So, or should be. But you can do also from tools import calculate area. When you write from X import Y, you're pulling that thing from the namespace X into the namespace of the broader. So if I do from NumPy import array, array is now defined in the namespace of the notebook. Array, I can go ahead and use array right here. Function is in the namespace. I don't need np dot array here, which is so that's the notion of a namespace. It's kind of like all the names that are inside of some Python. Okay, said a lot of things. I want to actually pause here and see what questions do people have. Okay, and I should probably, yes.
Can you, sorry, going to the tools thing, can you try dot import tools?
From dot tools import like that?
From dot import tools
Dot import.
and then get rid of the rest.
Oh, from dot import tools
Like from yeah.
that.
the-
Well, let's see if that works.
Yeah.
Nope. Tempted relative import with no known parent package. This kind of syntax works when you're in a package.
Okay.
Yeah, this you can write inside of from dot import circle. So it works here in the context of, yeah, it's a weird syntax that you might not have seen in a lot of code. From dot import circle works in the context of a package. But as you can see from this error, doesn't know what the parent package is. So this is called the relative import, or relatively obscure thing. Yes.
You had to the Y and now you have to folder and inside circle down.
Yeah.
Both should work.
Both should work, and none of them work here for some reason that I don't understand. But both of them should work. So, like I said, the Python looks, when you type import tools, it looks first for a py file called tools right there. If it doesn't find that, it will look for a package called tools. And a package is a folder with a dunder init file. It'll look for a package in that folder. Again, it'll look right locally where you are for that package, tools. And if it finds this folder here with the init, it's good. If it doesn't, I don't know why. But if it doesn't find it here, then it will go to your Python path and look for it somewhere on the path, right? And after that, it will give up and say, I can't find this, and raise an import error. So that's the order that it goes. And so now we'd like to go to the next step, which is to say, okay, now we want to get things into the Python path. One way is to give it to every person that we know that wants to use this thing. Let's say we're in sort of the mode where we want to collaborate with many people on this, and say, hey, you should copy this into your Python path. Here's a file. Here's a package, right? A folder with the dunder init file. Copy it into your Python path and it should work. And the truth is it should. The problem with this approach is that it will cause a mess invariably. And that's because different computers have their Python path, their installation, the way of installing software set up in different ways. And so it's really quite risky to say, here's a folder, drop it somewhere inside of, where was it? Like inside of /srv/conda envs notebook lib Python 3.11 site packages, which is a folder you should never visit really. It's risky to say, hey, take this and drop it in there and it should work. And maybe it should, but it will cause a mess. Invariably, you'll end up with all kinds of clashes. And so Python has a systematic way of installing packages. Who here has installed a Python package on their computer? Okay. Out of curiosity, who's used Conda for this? Who has used pip? Okay, and those are package managers. And the nice thing about these package managers is that they manage the environment for you and they manage the installation. So when you type pip install pandas, for example, in a particular environment, it knows, oh, I'm in this environment. For this environment, the Python path should be the following parts of my computer. Let me put it somewhere reasonable within that. In fact, who here has uninstalled a Python package? Who's, let's see, using conda, using pip. Yeah, so you can type pip uninstall, which is a lovely thing to do, and it will know where to go. That's part of the problem of copying something somewhere is later you have to remember where you put it, if you want to uninstall it and reinstall it and so on. So pip provides the package managers like conda, like pip, they provide for you mechanisms to install packages, to update those packages when needed, to uninstall them if needed, reinstall them if they're broken, stuff like that. So we need to kind of follow certain conventions in order for us to be able to do those things. Let me go back all the way up here. So in my own computer, what I have is I have a folder called source. That's where I put source code. Source code, I think of that as, I guess, code that gets used elsewhere is one way to think about it. And we're going to start creating here a Python project that can be then installed, and I'll walk you through some of the machinery of that. And hopefully I'll show you also how to test the code, which will become important. So let's call this project geometry. And there's sort of a standard way of defining these things. So I'm starting a blank canvas here, which will be my my project. I will use the terminal out of an abundance of care. We'll come back to this notebook later and see how this all melds together. But for now, we're going into, oh, here, source geometry. And in there, I will touch under init. Sorry, let me. In fact, I will make a directory and call it src. And I will go into src and I will touch geometry. And no, that's not what I wanted to do. RM geometry. But to make their geometry. So we're building a real edifice here. Notice that we have a source directory in here. There's something called geometry. Inside of that, there's something called src. Inside of that, there's again something called geometry. And in this geometry directory, we will touch a dunder init.py file and also a circle.py file. You also, so you can see how this goes. I have my source directory. Inside of the source directory is where I develop all kinds of libraries. So this library is called geometry, which is the next item here in the path. And inside of geometry, I have a place where I put the source code for this geometry library. Inside of that, I will put a package called geometry. It has a dunder in it and circle.py. I will go back to my projects, into blob calculations, tools, and I will copy the code that I put into the project now into this library that I'm creating. Right here. So I have that, and that's all good and nice. So I've created the structure here for the, let me show you this in the book because I think that'll be helpful. Right, here it is. So I've created the structure. Up here is where the source directory, where I put all my code libraries, and I have like this library. So this is now a library in the sense that it could have multiple different modules or packages. And in this case, there's one. And then around that, I will create other infrastructure that I need that relates to the management of this library. So I will I'll start with this one called pyproject.toml. I'll actually copy it straight from here. You know what, before I do that, I will create one more folder that I haven't created, and it's pretty important here. Yeah, I'll make the tests directory. So now I have really what is in here. So I have geometry, I have all the source code, and then I have separately somewhere where I will put tests in the fullness of time very soon. And this PyProject, I'll start with that one. Let's populate that one. Is a file that's used by what we call build systems. Okay, I'll put all this stuff in here. So the PyProject is a set of metadata about the package. When you type pip install something, the first thing that pip, the package manager, will do, or conda install something, pip is a better example actually, is it'll look at this file and say, okay, what do I need here? What's the metadata that is required in order to build this? It'll look for what's called the build system. This is a TOML file. TOML, I believe, stands for Tom's markup language. Very egocentrically named. It's a very nice language for metadata description. You can think of it like a Python dictionary, where these are keys up here. Inside of different sections. So these are sections of the file, like the section for the build system, the section that describes the project, the section that describes project URLs and other things. You can put sort of these key value pairs like name equals geometry. In this case, for example, for the project, this build system is a little bit about like, how do you build this software? In this case, we're saying use some library called setup tools. There are multiple options for this stuff. It gets a little complicated, but the build system we want to use for most Python projects is probably setup tools, unless you're building something really complicated that has C extensions or something else. And there's a build meta backend that is the one that's kind of the most generic one. So that's the one we're using here. Here we're generating some metadata about this. The name is geometry. You can add a dictionary with authors of this. So as you're developing this with others, perhaps you add the names of all your collaborators. A description, maybe there's a README file. There should be a README file, which we'll add in just a second. .markdown that maybe contains more information. There are these classifiers. Classifiers are used by directories that contain Python packages. For example, the Python package index, PyPI, from which we install a lot of Python packages, it's got these classifiers so that it can assign, to kind of classify the different libraries. This is a pretty good set of stuff if you're doing scientific computing. Like you want to tell it which programming language is this. It's Python, which version. We're going to be doing Python 3. What kind of license? That's kind of useful if somebody's searching through one of these indices and wants to find only things that have OSI approved licenses, the open source initiative approved licenses. We'll talk about the license in just a second, so on and so forth. We're going to say this requires Python above some version, and then we can specify all the dependencies. And this is nice because now in a package manager, and this is one of the things that can go very wrong when you install this by hand, you give somebody a folder and say, hey, copy it somewhere on your machine, is that if you require a particular version of pandas in their environment, they might not have that. But if you're installing this using a package manager, the package manager will look at this. They'll say, we'll go to this dependencies specification. They'll say, oh, these are the dependencies for the package. Let me get those dependencies for you. And so if you've installed using one of these things, you see that, you can kind of see like, oh, it's getting one thing and then saying, oh, I need all these other things. And then it installs, you get this long thing when they're installed.
in an environment involved.
Sorry, can you repeat that?
What happens when in an environment you install multiple packages and each package has a different dependency?
That's a great question.
Right?
Yeah, so let me just repeat that. The question is, what if we try to install into the same environment multiple packages that have conflicting dependencies? For example, I have one package that has pandas equal 2.2.2 and another one that requires 2.2.3. The answer is usually the later one is the one that's gonna win, but sometimes you'll also get just errors conflicting kind of, and that's one of the reasons that you want to use an environment manager like Conda, which lets you install, create separate environments into which you can install separate packages. If you have a conflict between two packages, install one into one environment, another one into another environment, and you can happily run each one of them in its own environment. So that's kind of under the topic of virtual environments. Okay, all this metadata here is beneficial because once we have this metadata in place, we can start using a package manager in order to install this. And in fact, we can give this to others who can also install this. Let me just complete the kind of full picture here with a few more tiny details. One is, so you see there are a few files, other files. Let's start with the README file. Maybe I have an example of a README file here. Yeah, here is a good README file. So I'll copy that one here. And I use the markdown language to write the README file. The README file should explain roughly what this thing does. Sometimes it'll include additional documentation, how to install this thing, how to contribute is a good idea, how to get help. READMEs can get really elaborate, and it's a good idea to elaborate them unless you're writing separately, also writing documentation, something that we won't look at today, but we can look at later on in the course. That's
This file supposed to be in the geometry folder?
It is not. No, the structure that I'm following is the structure that I have here, where inside of the source geometry, I have only my Python packages. So this separates kind of this metadata stuff like this from the source. In fact, it also separates the tests from
You're
the
in
source.
source file folder, and there's a geometry folder.
Yeah, it's a little confusing. There's like so I'm in source. Oh, I did the wrong thing. You're right. I need to move all of these in here. Thanks. Yes, you're right. So this needs to be right in here, right next to the source, the tests, and then a metadata. Thanks. The other thing I'll add in here now is, so where am I? Geometry. Okay, now we're in the right place. I will add a license file. We won't talk a lot about licenses today, but one thing that you should know if you're writing code and sharing code online is that, at least by US copyright law, this copyright law protects creators rather by default. So if you put something up online and it doesn't have a license, then it's all rights reserved, meaning in practice at least, or well, not in practice, in theory at least, it means that nobody else is allowed to use this thing that you created. And you can sue them for a copyright violation if they use it in certain ways and so on. So, if you're surfing GitHub and finding code and it doesn't have a license, in principle, it's you've got to be a little careful about using it. And so, the kind of license that I will usually use is something like the MIT license. Because I'm not a lawyer and don't know what to do, I go to others who are lawyers and ask them. In particular, there's something called, I mentioned that before, the Open Source Initiative, and they've come up with a list of licenses that you can use that they've looked over and said, oh, this license provides the following kinds of protections for the copyright holder, for the user, downstream user. This one is very minimal. I like it for that reason, but there are reasons to use others as well. And basically it says, It's free to use this and the documentation. You can deal with it without restriction. You can use it, you can copy it, you can modify it, you can merge it, publish, distribute it, you can do whatever you want, basically. Even you can sell copies of it if you want, and you don't need to pay me royalties if you do that. You do need to include the above copyright notice. If you're using this code, say you're copying a bunch of this code into your code base, you need to include, need to say, oh, this part of my code base is copyright Ariel, because he wrote that. And also, there's no warranty. Like something bad, you use this and something bad happens, that's your problem. That's kind of like very basic sets of protections for both sides here. So then we can talk more about licensing. There's a lot of ins and outs about that. Happy to discuss this further. But generally, if you're putting code out there on GitHub, openly, your intention probably is for other people to be able to use it, attach a license. Okay. So having done all these things, now I'll just go back to the Pi project and point out one more thing here, which is at the very end here. So I have some things about where kind of like web presences of this, and later when we do Git and GitHub, we'll come back to this because we'll put this. What I will be teaching is how to put this on GitHub and like collaborating with others on this code base. So that'll be later. For now, I'll just point out that we did also tell it where the packages are. So we were telling setup tools, this tool, a Python library that sets up Python packages, where the packages are or how to find them. So look inside of this directory called src, include everything you find under geometry, and exclude anything that you find under tests. So do not install the tests. This is also a benefit of this of the structure, that there are tests, so you can test the code, but the tests don't come with the installation. So if the tests are very big, they contain data and so on, they don't go to like the end user. This is something that developers can use in order to test the software, but doesn't need to go to the end. So that's kind of how we set this up here.
Where is the parent folder? And included the child of where? Is it like geometry is under the SRC, right?
Yes, that's right.
Okay.
Yeah, so it's going to look inside, it's going to execute some kind of function called find in the SRC folder, and it will include anything that's called geometry. Tests are not in there for now, but later on you might have tests in there as well. And this is just to tell it, if you find something called tests, don't install that. Okay, what questions do people have at this point? All right, so now we should in principle be able to do, and let's see if this works. Pip install. Dot like this. I believe that should work. So that's telling pip I'll be extra careful. Python -m pip install dot. This is actually a better way of using pip. The reason this is a better way of using pip is because you're saying this Python. When I type Python in this environment, I'm calling a very particular Python. As those of you who've used environment managers know, that you could have multiple installations of Python in various places on your machine. This says, I'm right here in this environment. When I call Python, it's that Python. -m is a flag for Python that says, there's a module called pip. It can either be something that you import, or it could be something that you run. Run it as a module. -m means run this thing. And then the rest is very similar to what happens when you type pip install without the Python -m. But this is a safer way of running Python, running pip. So to do that, let's see if it works. It would go then and do various things. So one thing that it did, and relates to the question before here, is it uninstalled pandas 2.3.1 that was previously in this environment, which is much more updated pandas, and it downloaded and installed Python 2.2.2, which is what I required in the Pi project. Now, let's see if the magic all works. Now I should be able to go to my project. I should be able to, I don't know, delete this folder altogether. Let's do that. That'll be fun. Oh, it's not empty. Okay, well, let me go there in my terminal. CD, projects, blob, calculations, RM. Yeah, okay, I'll go in there. Tools. RM circle.py, RM under init.py, render tools. So now I've removed the tools directory altogether here. That should be reflected soon. This is,
It says fail.
oh. What's in tools? Oh, of course. Always a night time. Okay, RM, don't do this. Okay. Now it should be gone. It's gone. Okay, now let's see if this all worked. From geometry, import, circle. Let me restart the kernel. Okay. Bam. And now I should have circle dot. I can't actually run that because this data doesn't exist, but the namespace does include circle dot calculate area, including its doc string, right? So now what pip did in that previous step is it installed the software into somewhere that it expected. I'm pretty sure, yeah, here it kind of tells you a little bit about where it put things, but mostly it just tells you, look, I've installed geometry 0.0.1. This is the version string that's defined here. This is a scheme called semantic versioning. Semantic versioning in the sense that it includes some meaning. So 0.0.1 tells the user this thing is going to change a lot eventually because it's very early days. If it's 2.0.3, then you're like, this is a pretty this is pretty well solidified software here. So it's about giving the user some message about, and if I went from 2 to 3, you've got to know that there's probably some substantial differences between 2 and 3 in terms of APIs and so on. So the version is a way to communicate with the user about what you did between different versions. But there is geometry 0.0.1. I wonder, actually, we'll try a little bit more here. I can import geometry, and then maybe it even has, for example, something that sometimes happens automatically. No, there's no. I would have to insert this version. I was just curious if it gets inserted automatically, but it doesn't. So you have to do something to insert it. Okay. So that's kind of the full thing. Let me just pause here and see the question people have.
Poetry to create these, or do you always create these by hand?
I do what I just showed, which is like the very basic thing, but do you want to say a bit about poetry if you've used it?
It just does this automatically, basically creates like the files in the same format for you and creates the like tunnel and everything like that.
Yeah, so that's a way to do all this more automatically. I think there's more than one. Poetry is one of several of these systems that create this. I think there's something called hatchling, maybe. There are other kind of tools. Poetry is one that's quite popular. I haven't actually explored poetry a lot. I think going through this exercise of looking at all these things is helpful, because there's nothing, when you do something like this, you execute some CLI, some command line interface on your terminal, and all of a sudden all these files show up. There's something a little bit magical about this, and this was mostly an exercise in demystifying. These are files on your computer. There's some metadata in there. If the metadata is informative, something like pip knows how to take that thing, put it somewhere else on your computer, such that when you type import this thing, the namespace shows up and off you go. And so now I think you have sort of the conceptual, hopefully, or if not, then we can discuss this further. A bit of the conceptual structure of what Python does when you type import and how you can put your own stuff in there. Hopefully you see this as something you would like to do, maybe useful if you're collaborating with others. The first step is, and we'll do that later today, is to put this stuff on GitHub. And then you can point people, you can update it with Git and GitHub, you can collaborate with others, you can point other people to that Git repository and say, this is where the software is, you want to install it? download this thing and type pip install dot inside the source directory or inside the top level directory of this thing. And that works pretty well. There's a second kind of level where you upload this into one of these. Well, let's do DiPy. You'll hear about DiPy from Serge tomorrow, I believe. Where you put it up on something like PyPI, and then you cut out the whole Git and GitHub part of it. You don't tell people go to GitHub, download this thing, and then run pip install in the top level directory. Instead, you say run pip install DiPy, and it will go to PyPI or wherever this is, and it will get it. And it's not too hard to do either. You create an account here, you put your software up. If it's got semantic versioning, it'll create this release history that contains the semantic versions. You can go and install different versions. If somebody else depends on your software and depends on a particular version, they can put in their Py project, I don't know, DiPy version 110. That's what I require. And then when they install their software, it will get the right version from here, and everything will beautifully just work. So that's a second step. Now, this entails all kinds of socio-technical consequences. People will show up and say, hey, you put this software up and it doesn't work for me. Can you fix it for me? And depending on what you want to do with this software, you could say, well, that's great for you and good luck. Or you could say, hey, I put this software up and I intend for you to use it and let me figure out what's wrong. My kind of philosophy for some of these projects, at least like DiPy, is it's great if a lot of people use this because they will figure out what's not quite working. They will tell me what kinds of things other people need. There's kind of a further layer of fame and fortune involved that involves maybe publishing papers about your software and then other people going and citing that I'm a co-author on a paper about this piece of software that's been around for a while. And it's by far one of my most cited papers. Like there are two papers that I'm involved in. Both of them are about like these kind of resources, and both of them are like well above the other papers in that are about all kinds of scientific findings. And that's because it's a tool. Many people use the tool. And so that's, I don't know, fame and fortune is maybe a bit overblown, but it's useful for me in my career. So if you see this as a niche that you're interested in, you can consider how you make that niche beneficial to your career path. Okay, let me see. What questions do people have at this point? Sorry, I threw a ton of stuff in a rather zigzaggy way today. If you're interested in trying this out, next week would be a great opportunity to say, hey, let's develop a software package that does X and try all this out. Before we close, seeing no questions, let me just say one more thing about testing, which I think is going to be useful. We'll come back to that also over the course of this event in the future. So one more thing that I'd like to point out, and Russ kind of pointed that out in both of his lectures, so I wanted to sort of emphasize how this is done. The mechanics of this is the importance of software testing. Russ talked about test-driven development. What I described here is not test-driven development. It's more like analysis-driven development. I'm doing some analysis, and in the course of my analysis, I develop some stuff, and eventually it shows up in a package. And I think this is sometimes the way things work. Sometimes it's very hard to say in advance. The function that I will need is one that calculates the area of a circle, therefore let me come up with tests and then write the code. If you can do that, that's great. But if you can't, then you might have to go back and write your tests in after the fact. So let me go back to my source geometry folder and point out this tests folder. The thing that we use in order to write tests are what are called test harnesses. Particularly, I think we have PyTest here. Oh, no, we don't, but I'll install PyTest here for now, and we'll install it into the hub later so we all have it. PyTest is a software library that also is what we call test harness. When you run PyTest in your source directory, it looks for a a folder called tests or folders called tests. It looks inside of those for files called test underscore something. And inside of those files, it looks for functions called test underscore something. Let me demonstrate. Touch tests, test circle .py, and open that up. From geometry, dot circle, import, calculate, radius, def, test radius, r equals 1, calculate radius, r, right? This should be true. Okay, so the structure of a function or a test is, it's got some definitions of calculations, like calculate radius. I'll just make this more explicit by saying, no, this is calculate area, sorry. Well, this should be test area. So it will have some definitions, kind of like base conditions. It will have a calculation. In this case, we're using calculate area to calculate something. And then it will include what are called assertions. So the assert statement in Python is a statement that is, this is a keyword in the language. It's actually there in the namespace. It's always there in the namespace because it's part of the language itself. It has the structure of some logical statement here. And if that logical statement is true, it does nothing. Otherwise, it will raise what's called an assertion error and say, raise the string. Is something like that. Right? So, and I can test my code again by writing PyTest here. And now it went from no tests to one test, and it passed because it's correct. I can demonstrate what happens. Let's say I just say area equals 1 here. So I planted a wrong answer here. And now it will raise the error. It will fail. It will say the calculation is wrong. And it'll say also, I tried to assert that 1 equals this number and it's not. And it comes back with this red thing and with the test failure. So that's a basic mechanism of tests. I wanted to show that, because it's really important, and kind of plant that seed. We don't have a ton of time now because we're basically almost out of time here now. But this is, I think, kind of the next step. Once you develop software, like I said, and share it with others, putting tests in place will really, really help you. Because as you elaborate the code, you can add additional test cases and say like, you can, for example, you can say, what happens if, so this we've asserted, you can add test cases, r equals -1. What should happen in this case, for example, if I do area equal calculate area bar, right? You come up with an idea of what this should be, because a negative radius is possible. Maybe this should return not a number, maybe it should raise an error. This is starting to do test-driven development. Come up with some idea about something that could happen in the code, and I'm saying, okay, what do I want? And I can assert that thing here. I can say, for example, assert area equal, I don't know, np.nan, for example, in this case. Should be a nan. If you gave me a negative number, I'll give you a nan. Or you can do more complicated things to make sure that an error of a certain kind is raised. So this is where you start elaborating the code. It's also nice if somebody shows up and says, hey, there's a bug in your code. It's nice to put the bug in your test first, just to confirm that the bug exists. And then once you wrote the code that solves the bug, the test should pass. And now you have a test in there, making sure that that bug doesn't come back. That's another way we can use code as tests in order to keep advancing the development of software. And I just showed kind of the most basic thing. There's a lot more elaboration to this, which we can play along in the coming week and a half. Okay. What questions do people have about tests? That was a very brief I want to just show that for completeness. All right, if no questions, then let's stop here. Go with lunch. We will resume in 90 minutes with Git and GitHub. Good.